Good afternoon. During the lecture of today, we talked about surface area. In order to do this, I need to recall the notion of area distortion of a linear isomorphism. So suppose that G defined on nu with values in nu tilde is a linear isomorphism between two-dimensional subspaces of R3. Then we define the area distortion of G as the quotient between the length of the cross product of GV1 and GV2 and the cross product of V1 and V2, where V1 V2 is a basis for nu. Now let's consider a surface patch sigma defined on U contained in R2 with values in S, where S is a surface. Then let Q a point of view and P be the image of Q by sigma. Then if we use this definition here for the basis E1, E2, then we can compute the area distortion of the map d sigma at Q, which is defined on R2 and takes value in TPS. So according to this definition here, we have that the area distortion of d sigma Q, this is the quotient between d sigma QE1 multiplied by d sigma QE2 divided by the length of E1 cross product E2. But this expression can be simplified because this is an orthonormal basis, so the denominator is 1, and we use the fact that d sigma QE1 is nothing but then the partial derivative sigma u q, and d sigma QE2 is a partial derivative sigma vq. So the area distortion of this map reduces to sigma uq times sigma vq. Now we are ready to give the definition of area and the definition of integral of a function over a region of a regular surface. So definition: 3.55. So let S be a regular surface and let R be a region of this surface. Then we call R a polygonal region. If R is covered by a single coordinate chart, sigma, defined on an open set U over 2 with values in S as usual, and sigma inverse of R equals the interior plus boundary of a piecewise regular simple closed curve in R2. So we can define now the area of R as follows. Area of R, this is given by the double integral over sigma inverse of R of the area distortion of the sigma dA. Second, we can define the integral of a smooth function precisely if if f defined on R with values in set of real numbers is smooth, then the integral of f, the double integral of f over R, this is defined as the double integral over sigma inverse R of f composed with sigma multiplied by the area distortion of d sigma dA. This definition are for the case when the region R is covered by a single coordinate chart. So now we have to consider the case where R is the union of finitely many polygonal regions intersecting only along the boundaries. Then the area of R or the integral of a function f will be the sum over all the polygonal regions of the area or of the integral The next step is now to prove that the area and sorry, I prefer to write the surface area and the integral are well defined. The meaning of this sentence is the following. If you have two surface patches, you sigma I defined on UI with values in VI which cover R, then the integral of f dA and the area of R take the same value when computed with respect to either surface patch. I would like to point out that it's enough to prove this result only for the integral of a function, because if you give a look at the formula for the area of R, the area of R is nothing but then the integral of the function which is identically equal to 1. Now, in order to prove that this integral here is well defined, I need a lemma .57 that it will not be proved. So if psi is a diffeomorphism between open sets over 2 and phi smooth function on U2 with values in R, and K contained in U2 is a polygonal region, of the plane. Then we have that the integral over k of phi dA coincide with the integral over psi inverse over k of phi composed with psi multiplied by the area distortion of the differential, of the map d psi dA. Now let's prove the proposition uh, 3.56. The idea of the proof is that I consider an auxiliary function known as a transition map psi defined as a sigma 2 inverse composed with sigma 1. This map is a diffeomorphism between sigma 1 inverse V1 intersection V2, and I don't have space, between sigma 2 inverse V1 intersection V2. Now up to okay, let's maybe try to make a picture. Suppose that this is the surface S, this is the region R, and you have the map sigma 1 sending U1 on V1, and you have the map sigma 2 sorry, this is U2 sending U2 on V2. Then what I'm saying here is that the transition map psi is defined, of course, not on all of U1, but only on the set. Let's use another color. Let's use blue color. So if this is U1, if this is V1 intersection V2, then you have that sigma 1 inverse is, for example, this one, sigma 1 inverse V1 intersection V2, and you have, for example, the same here. This is sigma 2 inverse V1 intersection V2. But you can see from the picture that we can assume psi to be a diffeomorphism between U1 and U2, making U1 and U2 smaller. So precisely you can suppose that V1 is equal to V2. So you shrink the images of U1 and U2, and automatically you are shrinking also U1 and U2, and you get that these two sets are exactly U1 and U2. Okay, now I have to erase this formula. And what I have to prove is that, so we have to show that the double integral over sigma 1 inverse R of f composed sigma 1 multiplied by the area distortion of this map is equal to the double integral over sigma 2 inverse of R of f composed sigma 2 area distortion of this sigma 2 dA. Why? Because this is the integral over R of f dA computed using the surface patch sigma 1, and this is the integral over R of f dA computed using the surface patch sigma 2. We have to prove that they are equal. Now the idea is the following. First of all, we observe that sigma 2 is equal, sigma 1 is equal to sigma 2 composed psi, and the chain rule allows us to write d sigma 1 as a composition of the derivatives of sigma 2 and psi. So precisely you have that d sigma 1 is equal to d sigma 2 composed with d psi. Now in this formula we have the area distortion of d sigma 1. So the area distortion of d sigma 1, this is equal to the area distortion of this map. But it's possible to prove, this is actually an exercise which will be proved by the teaching assistants, to the product of the area distortion of sigma 2, d sigma 2, multiplied by the area distortion of d psi. So let's use this formula, and we get that this double integral here becomes the double integral of f composed with sigma 2 composed with psi, because sigma 1 is sigma 2 composed with psi, multiplied by the area distortion of the sigma 2 multiplied by the area distortion of the psi dA. Now to prove that this is equal to this, you have to use the lemma 3.57 and it is done. Okay, now let's see two examples of application of this formula. One, we have the area of a graph so we have a function f defined on an open set of R2 with values in R. Then you know that the graph G of f is covered, of course this map must be smooth, is covered by a single surface patch given by the following formula: sigma of x y equal x y f of x y. So what is the area? The area of R region contained in the graph G. So we have that the area of R is the double integral of sigma inverse R of the area distortion of the sigma dA, but the area distortion is sigma x times sigma y. Sorry, it's the length of sigma x times sigma y. And if you make a computation, you will get square root of fx squared plus fy squared plus 1. So the area of R is the double integral over sigma inverse R of fx squared plus fy squared plus 1 dA. Second example is a sphere we know that the sphere S2 minus an arc of a great circle. I mean an arc of circle of radius 1. is covered by the surface patch sigma defined by this formula, sigma of theta phi. This is sinus of phi cosinus of theta, sinus of phi sinus of theta, cosinus of phi, where u is 0 to pi multiplied by 0 pi. So essentially the idea is that we can use the formula for the area I presented before to compute the area of this subset of the sphere, and the value we will get will coincide with the area of the entire sphere, for the simple reason that the arc of circle we removed has area 0. Okay, we observe that the area distortion of this sigma is given by sigma, the length of sigma theta cross product sigma phi, and some computation show that this is sinus of phi. And the area will be then the integral of sigma inverse r of area distortion of this sigma dA. Now sigma inverse of r is u. The area distortion is sinus of phi, and dA is d theta d phi, and this integral here is 4 pi. Please observe that here a remark is in order. Essentially, here we are treating the boundary of u as it were part of u. So if we want to be rigorous, instead of writing this way, I should write this integral as the limit as epsilon tend to 0 of the integral from epsilon to 2 pi minus epsilon of the integral from epsilon to pi minus epsilon of sinus of phi d theta d phi. And of course, since this function is nice enough, you will get the same result. Okay, the next proposition I want to present is the proposition .60. So if if F is a diffeomorphism between two regular surfaces, and R containing S1 is a polygonal region, then F of R is a polygonal region of S2, and the area of F of R is given by the double integral over R of the area distortion of the F dA. I leave the proof to you because it's very similar to the proof of proposition 3.56. So we save time this way. And now let's talk about isometries and the first fundamental form. Okay, first of all, let's fix the notation. So suppose that S is a regular surface P is a point of S, then when I write this way, this is the restriction of the inner product to pairs of vectors in TPS. Remember that the inner product is defined for vectors in R3. So this is the restriction of the inner product to vectors in TPS. Similarly, I will write this way. And this is the restriction of the norm of vectors to TPS. Then we are ready to give the definition of first fundamental form 3.61. So the first fundamental form, I will write FFF of S assigns to each P in S the restriction to TPS of the squared norm function in R3. In other terms, is a map the map from TPS to R defined by X is sent to X squared P. Now, the definition of first fundamental form allows me to introduce the notion of intrinsic measurement a measurement if you don't like this word, you can use for example the word quantity. A measurement or a quantity defined on a regular surface is said to be intrinsic if it can be described in terms of the first fundamental form. Let's see, for example, why the inner product of vectors of TPS is intrinsic. Why this is true? Because there is this formula. The inner product between two vectors of R3, this is 1/2 multiplied by the square norm of X plus the square norm of Y minus the square norm of X minus Y. Clearly, this formula holds true if I consider the restriction on TPS so I was able to write the inner product between vectors of TPS as in terms of the first fundamental form evaluated at X, Y, and X minus Y. Another example is the one of angles. So angles are intrinsic. Why? Sorry, I made another typo. Why? Because you know very well that the angle between two vectors in R3 can be determined using this formula. Inverse of cosinus evaluated at the inner product of x and y divided by the product of their norms. So of course this formula holds true if I consider the restriction to TPS. So I just write a P here, a P here, and a P here, because I'm assuming that x, y belong to TPS. So I was able to write the formula for the angle between two vectors in TPS is a function of the inner product restricted to TPS and the norm function restricted to TPS. Now, if you use again this formula and the fact that this can be written as the square root of the first fundamental form, you prove that this statement is true. Another quantity which is intrinsic is the area of a parallelogram spanned by vectors of TPS. So the area of a parallelogram spanned by two vectors in TPS is intrinsic. Why this is true? This is true because the area of the parallelogram can be written using the formula for the length of the cross product, which is known to be the square root of the square norm of x multiplied the square norm of y minus the square of the inner product between x and y. Once again, if you consider vectors in TPS, this formula can be written as the previous one by adding the bottom index p everywhere. And once again, I was able to write a formula in terms of only the first fundamental form. Why? Because here you have the first fundamental form of x evaluated at x, the first fundamental form evaluated at y, and once again you can use this formula for expressing this inner product in terms of the first fundamental form. Now we will try to be more rigorous, and our goal is to give a precise definition of intrinsic, that is a definition in terms of mathematical objects. In order to do this, I have to introduce the notion of isometry. So let S1, S2 be regular surfaces. Then a diffeomorphism F from S1 with values in S2 is called isometry if the map df preserve their first fundamental form. That is, I have this identity, the square of the norm of x restricted to TPS. This is equal to the square norm of DFP evaluated at x for all P in S1 and x in TPS1. There is a statement which is equivalent to this one. Equivalently, we can say that F is an isometry if df preserve the inner products. What is the meaning of this sentence? The meaning of this sentence is encoded by this formula. This must be true for all P in S1, X, Y in TP S1. Clearly, this is equivalent to this one. Why? Because you can get the square norm of X as the inner product of X with itself, and you can get the inner product of two vectors using the squared norm function using the formula I used several times before. That is, sorry, I lost a sheet of paper. Using X, Y, P equal 1/2 X squared P plus Y squared P minus X minus Y squared P. Okay, the next definition, which is related to this one, is a definition of the definition of isometric surfaces. So two regular surfaces are isometric if there exists an isometry between them. And now I can give the definition I announced a few minutes ago. So a measurement is said to be intrinsic if it is preserved by isometries and the reason why this equivalence is true is a consequence, once again, of this formula. For example, let's explain why the area of a parallelogram spanned by two vectors of TPS is intrinsic. If f from S1 to S2 is an isometry, then it is true that the FPX cross product the FPY is equal to X cross Y. Why this is true? Okay, I should write here P, F of P. Why this is true? Because you use the formula for the length of the cross product of two vectors. I mean this one. Square root of A cross B. This is, sorry, excuse me, I made a mistake. Square. So you use that formula with A equal to this vector, B equal to this vector, and then you write each term you have here, I mean this term and this one, in terms of the first fundamental form evaluated at dfpx, dfpy. Then you use the fact that f is an isometry, and you will find immediately that this is equal to the length of x cross y. Okay. Then the next result says that it's easy to find examples of isometries because the rigid motions we studied before are isometries. So let's be more precise. So if f is a rigid motion over 3 and S is a regular surface, then f of S is a regular surface, and F restricts to an isometry between S and f of S. So this result says that the restriction to a surface of a rigid motion is an isometry. Now, how to prove it? I would like to give at least the idea. The idea uses a result, the proof uses a result we presented in the past. And you know that if f is a rigid motion, then f can be written as TQ composed with LA, where TQ is a translation by Q in R3, and LA is the linear map associated with the orthogonal matrix A. It's immediate to prove that a rigid motion gives you a diffeomorphism. What is more interesting is to prove that the restriction to the surface is an isometry. How to prove it? we can prove this using the fact that a map is an isometry if the map df preserves the inner products, for example, now what is df if f is a structure? Simple, is the composition of dtq with dla, but this is a linear map. Sorry, tq is a translation, so the differential dtq is trivial. Instead, DLA is a linear map, so the map DLA coincides with LA. So DLA equal LA because LA is linear. And now you have to use a property, use proposition 1.55 number 3. Property number 3, which says that LAP, LAQ, this is equal to PQ for all PQ in Rn. So this identity says that the differential of LA, which is LA, preserves the inner product. This is exactly what we need. Actually, this says much more than we need, because we have only to prove that df preserves the inner products of vectors in TPS1. Instead, here we have that DLA preserves inner products of vectors in R3. So essentially it's done. So this is the idea of the proof. Now I want to show you one example. Which allows you to understand that, of course, there are isometries which do not originate from rigid motions. So rigid motions give origin to isometries, but there are isometries which do not originate from rigid motion. So we have the following example. The cylinder surface patch is an isometry. So consider the surface patch sigma defined on U with values in C, where U is minus pi times R, and C is the unit cylinder with the vertical axis, with axis given by the z-axis. Sigma uv is equal to cosinus of u, sinus of u, v, and we want to show that sigma is an isometry. In order to do this, we observe that if Q equal UV is an arbitrary point, then sigma U at Q is equal to minus sinus of U cosinus of U 0. Instead, sigma VQ is equal to 0, 0, 1. So these two vectors lives in T sigma Q of C, clearly, and they are an orthonormal basis. It is clear why they are orthogonal, and they have length equal to 1. So now let's look at TQU. TQU is R2. We proved this before, and its basis is given by E1, E2, where E1, E2 are the vectors 1, 0, 0, 1. So what is the action then of this map? Actually of its differential, the sigma? The sigma send the sigma send these bases into this basis. Why? Because this sigma E1 is a sigma UQ, the sigma E2 is a sigma VQ. So this sigma sends an orthonormal basis into another orthonormal basis, and this implies so let's write this sigma sends one orthonormal basis on an orthonormal basis. This implies that d sigma preserves the inner products. Maybe it's easy to see why. Or I leave it to you as an exercise. Okay, I leave it to you as an exercise. So implies sigma is an isometry. Try to understand why this is true. Instead, let me check how much time I have. Just 7 minutes. In the last 7 minutes, I want to show another example of isometry which does not originate from rigid motions. So consider the surface of revolution, which is obtained by revolving around the z-axis of this curve here. For example, this one. And consider the surface of revolution which you obtain by revolving always around the z-axis of this curve. This red part is exactly the same as this one. Instead, what about the yellow part? I mean this portion here and this one. They are obtained by a reflection. So this one is obtained by this one by reflection. So what can we say about these two surfaces of revolution? We can say that there exists an isometry between them which is which is the identity on the part of surface which is generated by the red portion of curve, and it's the a rigid motion on the yellow part. Why? Because the yellow part of surface this one can be obtained by reflection from the yellow part of the first surface, and what you get is the rigid motion. So I will write which is equal to the identity on the between the red parts and it is equal to a rigid motion reflection between the yellow parts. So globally, this isometry here is not a rigid motion. This example here allows us also to understand that the volume is not an intrinsic measurement. Why? Because we just found an isometry which do not preserve the volume enclosed. No, I should write the volume of the region enclosed by the surface. it is clear that the volume of the region enclosed by this surface of revolution is different from the volume of the region enclosed by this surface of revolution here. So this isometry does not preserve the volume. Consequently, the volume is not an intrinsic measurement. Okay, that's all for today. Thank you for your attention.